Software in number theory and for computing, and it will not be so highly technical that if you're not a number theorist, you won't get anything out of it. So hopefully it'll be of interest to everybody here.
Well, I hope so. Thank you very much. It's great to be in the University of Washington. I've come all the way here from the Seattle Warwick Hotel.
He's actually from the University of Warwick.
Yeah, I'm actually from the University of Warwick, but more recently from MSRI. So I'm giving this talk because William asked me to give a talk on this subject. I've never given a talk like this before, and I have no idea if it's going to be successful or really very boring. So please feel free to ask me questions as we go through. There's going to be no mathematics in this whatsoever, and in fact very little content altogether. Well, you'll see. You'll see. Anyway, it's going to be, and it's more of an entertainment. It's more of an entertainment. So I should start by introducing myself. So I'm a pure mathematician. I've been doing research in number theory for quite a long time, and I'm particularly interested in using explicit methods to solve problems in number theory, and that involves doing the computations. So I'm interested in using computational methods to solve problems in number theory, and then, by extension, interested in the development of algorithms in number theory themselves. So we use computers. So what is this talk going to be about? Well, there are really two parts to it, but they're kind of going to merge the first part into the second seamlessly. I'm going to start out by giving a rather personalized history of the kind of computing that I've done, and the reason I've done that is really so to illustrate for you, to you, especially the the young people in the audience, which is most of you, just how different things are now from what they used to be. And that will kind of merge into a kind of overview of how number theory software has developed. And I said 40 years, and I think I do actually mean 40 years or so. And so the message here is to tell you that things may not be perfect now, but just be thankful that you weren't around trying to do what you're doing today 40 years ago. Okay. So I have one picture in my talk, which I'll show you. But yes, so ask questions as we go through, please. And there's the picture. Does this remind you of anyone? I don't know. You have to guess which one of those is supposed to be me. Right. About 40 years. Right. 1970. A school friend of mine came in and started teaching me Fortran, and which was fun. I don't think I knew that computer languages existed before. He said, look, just write down these instructions and the computer will carry them out. I've never seen it. I was 14. And the reason why he turned up and started teaching me Fortran is that he got himself access to a computer, of which there weren't very many around in 1970. I'll tell you about it in a minute. So I sat down and came back the next day having written some kind of a computer program in Fortran. And when I say written, I meant, I had a piece of paper and a pencil and I just wrote down commands doing what I thought Fortran was trying to do. You can imagine how successful that would have been if you've never seen a computer program ever in your life. And it was to list prime numbers, so it's number theory. I told this story to Henri Cohen last week, and he told me the first computer program that he had written at age 14, and it was incredibly complicated and sophisticated. Mine was just trial division to try and find the primes up to hundreds. And then I decided to branch out and write a second program to compute GCDs, and I'd never heard of the Euclidean algorithm, so I tried to factor both numbers and look at all the exponents, and I got a complete tangle because, of course, the two numbers didn't have the same prime factors, and I just got totally confused. And I don't think that one ever actually worked. So this is how we had to produce our programs after writing them down on paper. We had to put them on paper tape. So you had a strip of paper tape that would maybe go, kind of the length of this room for a 30-line program or something like that. And so you couldn't read the program. It was just a pattern of holes in the tape. And you could feed it into a machine and produce a printout. And then if you wanted to edit one line, you went into an editor, and the editor read the tape in one programming line at a time and displayed it on the screen, and you could either keep the line or retype it or insert a new line. And then at the end it produced a whole new tape. And I mean, debugging is quite difficult in these circumstances. Things didn't get better for quite a long time. I did get quite good at finding primes, though. At least I thought I did until I had this conversation with Henri Cohen last week. But I was very proud because these computers could only count up to 32767, which I think probably means they were 16-bit computers. But I got up to higher than that, so I thought that was quite clever. But I didn't write a complete multi-precision arithmetic language, which is of course what we heard done by the same age. Still. And I had the printout, so that you can print out from a line printer, and I printed up on my wall. I had that on my wall for years. So the reason why we had access to a computer at all back in 1970-ish is that I grew up in Cambridge, England, and my friends, my father was useless, he was a linguist, so he didn't know anything about computers. But my friend's father worked in the Department of Geodesy and Geophysics, and they had a computer that lived in a caravan that spent 6 months a year out at sea plumbing the ocean depths, and the other 6 months of the year parked behind the Cambridge Observatory. And they let us in on it on Sunday evenings. So I used to cycle out there behind the observatory and let us into this caravan, where there was an IBM 1130 that took this paper tape. And it was a nice kind of, so it was an entire, it wasn't as big as this room, but it was an entire room for this tiny little thing, in modern terms. And so when you turned it on, the teletype chanted away and said, enter monitor control record job card group only. And there was exactly one right answer to that, which I now can't remember. But if you didn't tap it right, it just repeats the question again. So, and if and when the machine crashed, the method of rebooting it was to put this bootstrap tape, which was another strip of punched paper tape in a loop. You had to put it into the machine, and then there was a bank of around 30, maybe it was 32, toggle switches that you had to manually set to a certain binary pattern and then press a button, and it would bootstrap itself up. I don't remember all the details, my friend knew how to do it. And the memory of this, you're probably going to ask me, how many bits of RAM or whatever it had. I really can't remember, but I do remember that the memory was really a core storage of the original kind, that when you looked in through the holes in the side of the box, you could see tiny little donut-shaped pieces of metal strung on wires, and each of those that you could see was 1 bit. And that's why they were called core storages, because they're just portable core memories. And they're pretty slow as well. So I used Fortran for quite a while. I think I've read about Algol. Don't think I ever heard about any other tools at this time. Algol looked to me really exotic. It had indentation. I mean, good Fortran programs were all exactly 72 columns wide, with exactly 6 columns of, they still are, exactly 6 columns of margin where you put your line numbers. And they had words in boldface and things. Algol was really weird. So I did get one qualification in computing, grandly named General Certificate of Education, Advanced Level in Computer Science. And to do this, we had to go off to a local college because high schools didn't teach this sort of thing. And at the college, there was a slightly more advanced machine where we didn't have to use paper tape anymore, we could use punch cards. And this was great, because it meant that your computer program was a deck of cards, and every line of the program was 1 card. And it actually had printed on the card, as well as the punched holes in the card, it had printed on the card what the line of the program was, so you could tell which line was which. And if you made an error and wanted to change one line, then you didn't have to repunch the whole lot. You could just take a card out and put other cards in, which was great. It wasn't quite so great if you dropped the deck on the floor. Yeah, okay. And so we used to queue up outside this computer room, which is kind of special air-conditioned room, without holding our card decks, waiting for our turn. And when you went inside, this kind of holy of holies, you were allowed in and you put your card deck onto a reader, and it read the cards really quickly, and the line printer would go chuntering out. And if you had a compilation error, like you'd forgotten a semicolon or whatever, then there would be an error, and you would go back to the back of the queue, and while you were waiting, you would go and punch your card.
How long would it go until it times out? Like if you made an infinite loop, would it just kill you after a minute? Or?
Oh yes, there would have been a timeout. I had to ask special permission to run my program up to 108,000 on primes. And the director of the computer center came in and said, what on earth do you want all these primes for? I did a little, when I was preparing this, I did a little test. There's a computer breaker called PrimeGen now. And it's really quite hard to measure how...
Dan Bernstein?
Yeah, what's too small? I mean, 108,000. I mean, it'll give you the primes up to 10 to the 8 in about a tenth of a second or a hundredth of a second or something. And so it's rather hard to compare. This was slow. Anyway, by the way, that's my only qualification in computing at all. Everything else is completely amateur. The kind of things I programmed at the time, apart from primes, I think the most exotic thing I did was some graphical programming. I'd been learning about Fourier series. This is when I was about 18 or so, and so I worked out the general term of the Fourier expansion of e to the x, and then plotted the graphs of 1, 2, 3, 4. Thanks, impressed my school teacher, which was good. So the exercise for the class is to do this in the next 5 minutes in Sage. It probably took me weeks and weeks. Okay, Fourier expansions of e to the x. Okay. I have on occasion actually been paid to write computer programs, which was nice. I had a job before becoming an undergraduate. I was part of a grandly named thing called the Hematology Computer Project, which was the first ever. It was part of the Addenbrooke's Hospital in Cambridge, which was a big university teaching hospital. It was the first hospital in the UK to actually computerize its patient records. And that was a huge project going on. This is around 1975, and they had a little offshoot because the guy who ran the hematology department was father of a friend of mine, different friend, and he had all sorts of ideas of, oh, now we've got computers, we can do this, that, and the other. And he hired me actually for two summers. So if there was a whole year in Cambridge where every single blood sample that was analysed at the hospital for doctors and everyone around the city so the blood sampling was done on a machine that was online connected to the mainframe computer, and a Fortran program that I wrote analysed that somehow. I can't remember really what it was doing. It was all still in Fortran. Everything was in Fortran. And the other kind of thing I had to do in this job was to debug programs written by other people. As you all know, this isn't the most pleasant of tasks, and it was particularly unpleasant when there are several hundred lines of Fortran where you have masses of conditional go-to statements that takes you, several pages forwards or backwards in this huge printout. And the editing was all done with punch cards. That wasn't very nice.
How was the data stored at the hospital? It wasn't metal rings, was it?
It was the big magnetic tapes.
Oh.
Like in the old films where on the computer you have, well, we had those.
The bomb.
Yes, but 7-track or 9-track?
This stuff was important. I was relying on there being no one in the audience over 30. No, I can't remember. They did give me a magnetic tape of my own, because one of the things that I was allowed to do after hours, as it were, was to try writing my own programs, and I tried writing a game-playing program, and for that I needed my own magnetic tape.
So when you were debugging these, did they have stacks of the punch cards in the back that you would go?
Yeah, I had my program was kept, and we had all these.
The old ones were kept filed away somewhere.
Yeah, they were. I think for the university system, your programs were stored on the machine, but if you wanted to edit it, you changed your deck of cards and then kind of wrote it in again. You didn't do any kind of online editing. It was all offline editing. Okay, so then I became an undergraduate. There was no computer science department, or there was a computer service at Oxford then, I think. Just beginning. There were no opportunity to take any courses in computing whatsoever. There was numerical analysis, which then as now is quite strong on numerical analysis. So I didn't really start computing as a student until I was a graduate student, still in Oxford. And I started using Algol 68 for reasons I'll explain in a minute. And so the qualifying dissertation, this is after 1 year of being a graduate student, contained my first serious Algol 68 program, and this is now some serious number theory going on. It's not just listing all the primes up to 100,000, it's a table of the dimensions of customers of weight 2 for q square root minus 1 of all levels of norm up to 100, and if you don't know what it is, it doesn't matter. Unfortunately, they were almost all wrong. Well, you know what it's like. You have a deadline. You have to hand something in. They want a table of numbers. No, but there's a lesson to be learned here, because I was computing numbers that no one had ever computed before, and so no one knew they were wrong. And haven't we had some discussion like this on Sage Devel recently? That, if your program is the only one in the world that can compute these things, then you can't say, "Oh, I've checked this on Wolfram Alpha." You can't. Anyway, no, I mean, it did fix the bugs. The program wasn't terrible. I was still fixing bugs in that program about last week, actually, because someone said they wanted an extended table. Anyway, so.
Something that still works with L 68.
No, I did it. This one I did rewrite in C++. Essentially. I'll talk about sort of programming languages a bit. Okay, so when I was a graduate student, we were in a much better setup than we didn't have to use punch cards, paper tape, or anything like that. We actually had some CRT terminals. There were precisely 2 for the whole of the Mathematical Institute in Oxford for all faculty and students. And this connected, for some reason I remembered this, the communication system was called Gandalf. I don't know why. The main computer that we were talking to was across the road in the Oxford University Computing Service. And so there were 2 of these terminals, and you had to get in early to get one, because there were actually more than 2 people doing computing. And the great thing was to get the faster ones into the slower ones. So I don't think anyone these days knows what these numbers called baud were. I think it was bits per second. Roughly bits per second. And if you got the 100 baud one, then it was really tedious, because if you asked to say, show me line 100 of my program on the screen, because you would never ask for the whole thing. Show me line 100. You could see the characters would appear across the screen. And if you actually asked for 100 lines, then you could go and get a cup of coffee just while they were displaying on the screen. So that was the speed of the thing. But we did have a good editor, and the reason why I had a good editor was not because the system provided one. The editor provided by the system was actually totally useless. It was a bit like the one that used to come with DOS when DOS first came out. But there was a graduate student in mathematics who decided that we needed a better editor, and he went and wrote one. It was called RAID. Which stood for Random Access Editor, because you could jump to any line. And he called it RAID because it sort of made a better word than RAED. And I googled RAED last night and found there was something called, what was it? Something editor. Oh, I've forgotten now. Red. Anyway, some game playing program. There is something called RAED out there. No, it's not the same. Anyway, so this made it actually possible to sort of edit your program online by saying, go to line 100 and then replace this by this. It was a bit like a sort of interactive version of SED or something like that. And it was provided by a mathematics student, not by any of the professionals. And it was someone who never completed his PhD, because he spent all his time working with the software. Okay, that's it. That's quite useful. So that's what I was doing. Graduate student. And so the mathematics graduate students, there are several of them doing computing. So by now we're about 1979, 1980. When they first started giving accounts to students, they decided that one account on the computer would be enough for all of the pure mathematicians in Oxford. So my username was PMaths. And it was the same username for all of the pure mathematicians. So when in practice it was just me and Richard Finch. And when I logged in, I had to change into my directory as opposed to Richard's directory, because that's the end of the difference. And later they decided that that wasn't quite enough, and they gave one username to each faculty member. So all the graduate students of one faculty member would all share one account. So when I ran out of resources, as I did, I used to share the accounts of Peter Cameron's students, which is why some of my printouts say PMaths, some of my printouts say Cameron. The pure mathematicians all use Algol 68, and the applied mathematicians all use Fortran. And as far as I can tell, applied mathematicians still use Fortran. Pure mathematicians have evolved slightly since then. Although there's nothing wrong with Algol 68, it was a really, really good language. I'll come back to that. And I learned Algol 68 from my fellow graduate student, Richard Finch, William Mass. And he did write a multi-position package in Algol 68 and a package for number field arithmetic. I don't think it went as far as class groups and so on, but you could do work over number fields, which is very useful because I needed that for my PhD. So it was a powerful. It was very like C++. Actually, when Pascal was invented, it was invented to be an easier, simplified version of Algol 68 for use in teaching. And somehow Pascal sort of took off. Algol 68 was always very big in the UK and never took off in the US, which is probably why it died out. Anyway, so one of the things that Richard Finch had done, which I was able to use, is that he had programmed Tate's algorithm. So this is for computing conductors of elliptic curves. Doesn't matter if you don't know what that means. It's quite a complicated algorithm. He, for some reason, I don't know why, he had a Fortran program for doing this for elliptic curves over Q. I wanted a program to do this for elliptic curves over quadratic fields, so I converted his Fortran program into an Algol 68 program. And it worked fine. And a few years later, when I wrote a book which included a description of this algorithm, I gave a draft copy to Richard to read through, and he noticed that the variable names in the sort of schematic version of the algorithm that I gave in my book were exactly the same as the variable names in his 1980 Fortran program, and asked if that was a coincidence. And of course it wasn't. It was because I'd used his same variable names. And if you look at both in Sage and in Magma, the implementation of Tate's algorithm, you will find the same variable names being used for the same variables in the same places. And that gives you a clue to who wrote them, because basically I wrote both of those. So, I mean, they really are the same. There are a few extra things, but if you want, I can show you exactly which variables go back to the program. And the whole the strategy of how there's a nasty bit in that algorithm where you have to do a loop and there's a test condition, and you refining things together. It's all exactly as Richard's 1980 Fortran program. Okay, so I then moved to the US and found no one here had Algol 68 or used it at all. I spent a year in Ann Arbor, and so the computing at Ann Arbor, I think there was a big computer center somewhere, but no one in the mathematics department seemed to use it. In the mathematics department, there was one computer, it was an Apple II, a couple of floppy disk drives. And it had 2 disk drives, and when you asked to use it, then they sort of asked you what you wanted to do it for, and make sure you also identify the user. And they gave you 2 disks. One had the operating system on it, and the other was a blank one for you to put your own stuff on. I don't know how much did 5 1/4 floppy inch disks hold?
320 kilobytes.
320 kilobytes, something like that. Yeah. So one of those had the operating system. Those are the days. Well, except that the only programming language they seem to have on here that I'd ever heard of was Pascal, so I tried to write things in Pascal. And I did actually do some modular simple programming in Pascal on this machine, and managed to compute the first modular elliptic curve from its periods. But it was a really painful business, I found, programming this in Pascal, because you really had to reinvent the wheel. I mean, there were no complex numbers, so you had to write all the complex arithmetic, multiplication, division, cos and sine of complex numbers. You spent so much time doing that you had hardly any time to think about the interesting stuff. I was only there for a year anyway. So in the end, I actually did most of those calculations on a pocket calculator. It was quick. So then I moved to Dartmouth College. Now Dartmouth, this is in New Hampshire. Dartmouth was quite a kind of advanced place for computing. It's where BASIC was invented, and it's also the place where the first ever time-sharing computer, where different people in different buildings could log into the same computer. And they also had a lot of their system administration was done by undergraduates, which is also quite interesting. So I developed my Pascal skills, and I also started using Maxima, computer algebra package. BASIC was only really used for teaching. I think there were 2 things. You couldn't graduate from Dartmouth without being able to swim and being able to write a program in BASIC. Because one of the inventors of BASIC, John Kemeny, had been, president of Dartmouth for many years. Although when I was there, he retired as president. He was back in the math department. So Maxma, yes. Now this was something completely new that completely new world. You could multiply x by x and get x squared. Symbolic algebra. You could integrate, differentiate functions. And Dartmouth had a developer's license for this, which is good because it meant that it cost nothing on condition that you reported bugs when you found them. I did. I managed to invert a matrix once and multiply it by the original. It wasn't the identity. I still have a letter from the people at MIT saying, "Thank you, we've already fixed this bug." Okay, so I had some programs in Pascal, some programs in Maxima, and they were completely different machines, different operating systems, and they were connected to each other. I don't quite remember what sort of connection it was. It must have been some kind of FTP. So, for my project, I needed 2 bits of software, and I had difficulty getting them to talk to each other. I had to output, I think it was matrices of heck operators that I'd computed on one, and program the Pascal program, and then copy them across to the other one, and then read them into Maxima and do stuff there, and then copy stuff back. So that was all quite tedious, but we got stuff done. And then I came back to the UK, and all my programs were in the US, except the ones I'd had when I was a student. So I had some files in Dartmouth College and some files in Oxford, and I was in Exeter. And so how did I get my... You don't think of this now. I come here and I log into my computer back home all the time. It's no different from if I was at home. But, okay, there was one good thing here, and I had access to a computer that had the same compiler and everything that I'd done my graduate student work on. So I could revive those programs. I could get my files sent over from Oxford. I had to write a letter to the director of the Oxford Computing Service, and they copied those files onto one of these big magnetic tapes and put it in the post. The parcel arrived, and I handed that to the computer service in Exeter, and they read the tape and made the files for me. So that was really easy. It only took a couple of weeks.
Might be lower bandwidth than your 100 baud.
Yeah, maybe. But getting the files from Dartmouth turned out to be completely impossible. I wrote to the director of the computer centre there, and they thought about all possible ways of getting some files on a computer in New Hampshire to a computer in the UK, and there was no way. So they printed them all out. So I had all these Pascal programs I'd written, they printed them out, and they arrived in a big parcel at printer. And I was not going to type all those in again, and I had never used Pascal since. I mean, would you? So no, I never used Pascal again. I had L68, Algo 68. So I continued using Algo 68. Algo 68 is rather like C++ in many ways. You can define classes and overload operators. And I think I said a bit more about that in a minute. The book that I mentioned before has whole tables of elliptic curves in it, and they were all computed on this mainframe computer. This place at Southwest University's Regional Computer Center. It was in a different town. Had remote access. It was all batch processing. You could submit jobs and then pick up the output the next day usually. And that's how things worked. So why did I change from Algol 68 since I was quite happy with it? Well, first of all, the computer I was running it on was going to be shut down, and they weren't going to replace it. People in mathematics departments who did computing were beginning to buy PCs, which had compilers, and if they had enough money, some workstations. Some workstations were really expensive there. If you wanted to run Maxima, you had to have a Sun workstation, and I many times applied for funding to buy such a thing and never ever got it. No, that's not true. Eventually I did jointly with an applied mathematician. Okay. The other reason I changed is that people actually wanted to use my programs, and I said, well, here you are, it's an Algo 68, and they said, no, thanks. So I decided to switch to a language which everyone else would be happy with. And I also wanted to get hands on these machines that some of my richer colleagues were buying. And they didn't run Algo 68. Either there were no compilers or they were really expensive. Yeah, those days I remember with those Suns, if you wanted to print a text file, you had to buy special software to convert text to PostScript. Which was very expensive. Can you imagine that? And yeah. Actually, we did eventually get a laser printer in our department, but this is around 1985, late 80s. the head of the department thought, no, it's fine to have some PCs in the department. Laser printer, no, that's something that surely a central service should be provided. And eventually we persuaded him to buy a laser printer. Anyway, and I discovered C++, which seemed to be able to do everything that I had been able to do without this. Yay. So, of course I'd looked at C at that stage, but to me C seemed very kind of crude and low level, and I wanted to be able to do things like write A equals B plus C, where A and B and C were points on an elliptic curve, elements of a number field, or something like that. I didn't want to write add A, B, C, because the programs were completely unreadable. I mean, that's just me. So C++ could do that. You could, as could yeah, you could overload these binary operators. But I also wanted to use a mainstream language, so I didn't want to use anything really crazy. And the reasons for that, so that I wanted other people to be able to use my programs, and I wanted to be able to use other people's programs. And in particular, libraries that people had written, so I didn't have to reinvent the wheel. And C++ seemed to fit all of those criteria. Some people would tell me that, oh, but it's much less efficient than C, sort of overheads. But I convinced myself that that wasn't really true. And one thing that influenced me there was, at about this time, now in the early 90s, there was a project called LiDIA, started by Johannes Buchmann in Germany, and they had decided to use C++ code for a big library of standard number theory routines from multi-precision arithmetic, although they gave an interface to various other packages. They didn't reinvent the wheel there, but they had code for number theories and also for elliptic curves. They were interested in cryptography. They were using C++, and they were computer scientists, so they knew what they were talking about. And so they said, no, C++ is good and it's efficient. And so I thought, right, I'll use C++ and I'll use LiDIA. And I did for quite a while. Okay, and so on Bookman's recommendation. And there was an alternative around as well called PARI, which I'll talk about in a minute. But LiDIA was much easier. I found LiDIA much, much easier to use than the PARI library. And the reason really was because it was written in C++, not in C. So you had classes and overloaded operators, etc. Although LiDIA had all this functionality of number fields and so on, and even elliptic curves, I already had my own elliptic curve code. I didn't want to switch wholesale into LiDIA, because that would have tied me in really closely. If I'd sort of thrown away my own elliptic curve code and just started adding to LiDIA, then I would have been tied to that in a way that would have meant that I could have never kind of left it. So I ended up using LiDIA mainly just as a C++ front end for the multi-precision arithmetic, which was, I think, the GMP. And I think now there are other much simpler front ends to GMP. I mean, front end, I mean just a C++.
Could you say anything about your reluctance to use LiDIA in a way that would at all tie you into LiDIA? Clearly there's something more than you're saying.
Well,
I mean, they're doing so much. It's sort of like Sage, but with Sage you didn't have a similar reluctance. Can you say anything about that, or is it?
I'm still using my own code, even though I'm using Sage.
Yeah, but you're putting a lot into Sage, but with LiDIA you barely used it, really. I mean, when I wrote modular simple stuff, I depended on LiDIA big time, and I credited it.
Your hacker program used LiDIA, didn't it?
So hard to build from source. I mean, it took...
Yes, okay, it took a very long time to build from source.
And to port and stuff like that.
And they were not very responsive. I could say some of these things a bit later, as to why LiDIA kind of faded away. It was quite hard to get bugs put in. I got a student implementing a whole lot of stuff in LiDIA which they never ever did put into the LiDIA mainstream. And so that was a bit frustrating. But also I had a lot of my own code that I like being in control of my own code rather than have to submit it to some other place to get accepted. But then there weren't the LiDIA people were mainly computer scientists, so the elliptic curve functionality they were interested in was to do cryptography and elliptic curves over finite fields. And so actually Nigel Smart and I wrote quite a lot of LiDIA code on elliptic curves over Q. So there is some in there. But it was a bit of a slow process. Getting it accepted. So I had been writing my own elliptic curve code before I used LiDIA, and I just carried on with that. because I like the sort of the independence I have. Oops. Oh. Page down was no. I pressed end. Sorry about that.
Quick review. Before the quiz.
Where I got to C++. Sorry about this.
There it is.
Oh, okay. I was somewhere in there. Okay. Okay. I was talking to Victor Chuk once, and around that time, and I said that it was annoying because I was building this enormous library, LiDIA, and only using a tiny part of it. And he said, "Oh, well, if that's all you need, then maybe NTL will be useful for you." And in fact, he made some changes to NTL to make it very easy to use, just as a sort of interface to some multi-precision integer arithmetic library like GMP. And so then my C++ programs then developed in such a way that you could use either LiDIA or NTL. And I continued with that for really quite a long time. I mean, it's still all there in my code if you look at it in the ECLib. The version in Sage only uses the NTL interface, but there is a LiDIA interface in there. The code would be a bit simpler if I wrote that out of it. I just can't be bothered as it works. So NTL, number theory library. It has some stuff in it that LiDIA doesn't have, but basically it's much, much smaller. It does polynomials. It has multi-precision reals and integers. There's a lot of Mod2 stuff, which I don't use. So when Sage builds my code, it uses the NTL interface. Okay, so what happened to LiDIA? No, again, I think there are some lessons to be learned. I think it's one of the things we was interested in. They were quite a big research group, and they did have external members of their group. I was one of them. I mean, if you look at if you could find online a list of members of the LiDIA group, I think at least at some point they listed my name, because I'd contributed code to it. But it wasn't really it wasn't a good mechanism for doing that. It relied on someone there looking at what you'd written and deciding it was okay. And the people in that group didn't really have the right expertise. They were computer science. And sometimes, it took a long time to get a response. You got to know one person in the LiDIA group, and then they got their PhD and moved on. And then you didn't know who to talk to. So there wasn't a continuity there. They were all on short-term grants. Some of them postdocs. And their main responsibility was to finish their own work and move on, rather than to LiDIA as a project. And so there was a leader for the project, Johannes Bruckmann, but he was a bit of a worked at a distance, I think. He didn't sort of get his, roll up his sleeves and get down to things. He was a figurehead. That's the impression I got. I don't know if you disagree with that. Then there was also this licensing issue. I mean, I wasn't really aware of this at the time, but I see now that it's important. I don't really want to talk about licenses at all. But you had to agree when you use LiDIA. You had to agree to something. I forget quite what it was. It's because they reckoned that they were developing state-of-the-art cryptography code in it. So there was a kind of competitiveness. But it was very big and quite hard to build. That's also key. And if you only wanted just a little bit of it, that was of course, now they're all alternatives. So I found, although I kept on testing my code for both LiDIA and NTL, more and more I was just using NTL. So PARI, I mentioned PARI briefly. So in the from starting about 1990, this enormously influential, significant package called PARI was created by a group around Henri Cohen in Bordeaux. And the name PARI has nothing to do with Paris. They're from Bordeaux. They don't have anything to do with Paris. The PA stands for Pascal. They started writing in Pascal. And apparently it was Joe Buehler who persuaded them to switch to C. And William told me that something I hadn't heard, that they apparently had started using Maple and just found it too slow.
That's what Armin told me.
Yeah, okay. So they were developing number theory algorithms for algebraic number theory. And so they wrote this library for that. So again, this was a package written by number theorists, not by computer scientists. And I think it's quite interesting that the package I found most useful tend to be ones that are written by mathematicians rather than ones written by the computer scientists. Of course, there's a big overlap in those groups. Say that Grant Bernstein, for example, is so they wrote it for their own work. But then, when I asked him when PARI was released, and he said, "Well, released. I wasn't sure that when released was quite appropriate for PARI somehow." But he said, "I think they started giving it away in 1990." In fact, the first version of PARI that I had, he gave me I think it was version 1.37. He gave me on a floppy disk at some conference because I found an email in which I offered to send him back the floppy disk. Because, it's worth something, right? He said, "Oh, it's all right. We have others." And then the next year, the PARI 1.38 came out, and he said, "We now have this thing called an FTP server. You can download it. I don't have to send you a floppy disk anymore." And that meant it was much easier for other people to So there are these two names that go together. One is PARI and one is GP. GP is a command line interface to PARI. It's an interactive calculator type program. It's easy to sorry about that. It's easy to use and it's powerful. I think it's played a really, really significant role in experimental number theory for the last 20 years. There are lots of people who use it, plenty who are quite happy with it, don't use anything else, including myself. I've been sharing, the reason why I'm mentioning him such a lot, I've been sharing an office with him for the last 2 months, and he spends all day typing away, and it's all he's writing GP programs, and C programs, and so a lot of people, there's a lot of work that's been done in developing quite sophisticated programs in GP, and you can find them around, and they're very quality. They're written in various dialects of the GP language. I mean, some of them are written in very old versions and don't work with new versions and so on, but they're there. There are some mathematicians who use this a lot and don't use anything else. And the person I'm thinking of there, really wants to know what DZ is. Anyway, you can probably guess. You just don't want anything else. It does what they want. Don't want anything else. And people still use a 15-year-old version. They don't, not interested in upgrades. That's what they want. There will probably always be people like that who don't actually want to upgrade. So you've got these two things that go together, PARI and GP. I mean, they're really the same, different interfaces, I suppose. One's a library interface and one's an interactive interface. So GP is much, much easier to use. I think the number of people who actually write programs in C that use the PARI library is very small. You have to do your own garbage collection. It's horrendous. I think I wrote a program using the PARI library once. It ran very much faster, but it took me several days to debug. GP is interpretive, so it's slower, but it's much faster to write. So this is a common sort of tension in computing between ease of writing and speed, something that Sage knows about. And since 2002, there's been a solution for this in the PARI GP world. There's a program called GP to C, which takes a GP script, and if it is written properly, then it will convert it into a C program, and then you can compile it, and then you can even load it into your running GP session, and you can get a big speed up, a factor of 5 typically, or more, depending on the kind of thing you're doing. So you can now take a GP script, which is easy to write, and then use this compiler and get something that's fast.
Sounds like Cypher. Oh, very
I'm sure there are differences, and technical differences and so on, but to me this sounds very similar to Python versus Python. You have to do things properly, or it either doesn't work or it doesn't give you the speed ups that you want. And the same is true of Python. So in fact, one of the projects that I'd like to do this week is there are actually 3 GP scripts still in Sage. One is some scripts by Tim Dochitzer on computing values of else functions, and one is a program by Denis Simon, who was a student at Cohen's, about 2 descent on elliptic curves over Q and over number fields. And over the last few days, Henri Cohen and I, and 99.9% it was him, have worked on getting those GP scripts up to the state where GP to C can actually read them without complaining and produce a C file. And one of the things I want to do this week is to take those 2 C programs that he's produced and let Sage use those instead of using the GP scripts. So I think it will be, instead of using GP scripts, using the PXspec interface, and it will be faster, maybe not a huge amount faster, but faster, and it will be a bit cleaner than using the GP directly. Anyway, that's a project this week.
The other one.
Just okay, so who's behind PARI? I mentioned some of the names already. It started in this fairly small research group, about 4 or 5 people. This acronym, ADASIX, stands for Arithmetique Algebraique Experimentale, or something like that. And its development has remained centered in Bordeaux, and there are essentially 2 people who are the PARI developers. That's Karim Belabas, his first student, and Bill Canova. And it has a bug tracking system, a little bit funny to use, but it's there. It has a test suite. Contrary to some of the things you will read on Sage as well, it does have a large number of test functions that are tested before it's released. And every time you report a bug and they fix it, as they do, they add a test to the test suite. Okay. They probably didn't do that 10 years ago, but they do it now. They have mailing lists, very dev, very support, very announce, which again are slightly weird to use. You have to talk to a robot in Dan Penstein's office in order to get anything out of it, but after retrieving it from your spam box. But there's a very small number of people working on it. It's interesting to try and work out why that is. I had a look at the bug tracker to see who'd committed all the changes. And they were almost all by Karim or Bill, and there were a few by Igor Schein. Now, it's possible that some of these bug fixes have been actually written by some other people. In fact, in some cases, I actually know that to be true, because I know that Jaron DeMayer has done some. But he sends them, he emails them the fix. They don't have accounts, and so they do the commitment to the SVN system. So, yeah, well, as I said, very few people work on it. I think the PARI developers are quite jealous of how many people work on Sage, and they can't quite work out why it is that lots of people work on Sage development, and not very many people work on PARI development. But that's the case. PARI is used a lot in Sage. If you took away PARI, Sage would have almost no number field functionality, for example. It would be catastrophic. It's not going to go, it's GPL. So, in case you weren't familiar with this package, it's Sage uses it for a lot of stuff. And, of course, because it's been used a lot in Sage, lots of bugs in PARI have been found through by Sage users. And these get reported and they get fixed. So I think that the relationship between these two, they're doing different things, and it's a symbiotic relationship. I think each one benefits from the other. It's not a symmetrical one. Obviously, Sage is much bigger because it includes PARI. Yeah, I said that. I said that it relied on PARI entirely for all its number field functionality. I think there are probably some exceptions to that, maybe for quadratic field, but it's essentially true. So, what does PARI get out of Sage? Well, effectively, there are far more people using PARI now than there would have been without Sage, because lots of Sage users are using PARI, even though they might not realize it. And so PARI gets tested a lot. Every time Sage is tested, the PARI functionality is tested as well. And so Sage has contributed, not just to the mathematical code, but the build system, for example. Joe and Amaya again has given some, put some patches into PARI to make that work better. Okay, get on to it. So, I don't think PARI and Sage are competitors, they work together. What will happen if the PARI developers give up is hard to say, because PARI code is rather hard to read and maintain.
Yeah.
And so, I don't think it's going to happen anytime soon. So perhaps it's a vulnerability. Right, okay. But, so of course, coming on to Magma, the situation is very different. Magma is definitely a competitor, because, Sage says it's a competitor to Magma. It's a mission statement. So, let me just run through Magma facts for a little. It was released in '93, but before that, for years, there'd been this package called Cayley, which was big on computational group theory. So, Magma is not just a number theory package. I'm going to concentrate this talk because I had to cut out, I'm not going to talk about Mathematica, for example. I'm only talking about packages that number theorists use. Magma does far more things as well. In particular, group theory, because of its history and because it's John Cannon, whose name I didn't seem to put on this slide, but I should have done. He's a group theorist, and one of my colleagues in Warwick, Derek Holt, is also a computational group theorist, and they work together a lot. So actually, my own university has quite a close connection with the University of Sydney and the Magma group. John Cannon spends 3 months in my department every summer. Shared an office with Robert Miller last September. So I think one reason why there are a lot of number theorists who've been using Magma for years and who haven't switched to Sage, and the reason they usually give is Magma has very good support for algorithmic curves, surfaces, divisors, all that sort of stuff. And I think unless that changed, then those people are going to keep using Magma. So Magma's used a lot. They have 3,000 citations from research papers and books listed on the web pages. This is something they started doing quite recently. They got some students to go through and try and find all the references to Magma they could find after they've listed them. And patrolled by me, and there are at least double that by William. Not counting the reference to the Sage manual, which is
They list the Sage manual?
yeah, they do. They do. So, number theories do use Magma, you're going to continue to use Magma. If you know Magma, you know Magma. It's a strongly typed language, it uses its own language. It's not particularly hard to program in, but it's very hard to extend. You can't write your own classes, etc. And it's based on very, very pedantic abstract mathematical principles. It doesn't, when you start up Magma, it doesn't know what X is, you have to tell it for an array or whatever. It's free. Crucial thing is the source. The core functionality, the low-level stuff, is written in C. You don't get that when you buy it. You do, however, get a lot of the higher functionality, which is written in Magma's own language. You get to see it.
If there's more in C than that sentence suggests.
Is
There's
there?
over 2 million lines of C.
Okay.
A lot of higher level stuff gets rewritten in C.
Right. Higher level stuff gets rewritten in C because it's faster, and then usually deleted from the bitbook.
Yeah, exactly.
Yeah. So there's high level stuff in there that probably started out being Magma language code written by William, and maybe some written by me, and it disappears from the visibility. Of course, but they, like Mathematica, they don't hide what their algorithms are. It may not give you as much information as you would like when they have really good algorithms. But if they're using so-and-so's algorithm, they're using so. They have a very complicated way of describing how they do 2 descent on ellipticals over Q, for example. They say that they have their own implementation of the method that microgram uses. They don't say that it's important, which is wrong. But I've never seen the microcode ellipticals over Q, although when they were writing it, I was in kind of daily communication with the guy who was doing it, which is clear. A lot of Sage developers use Magma. Try that. I bet William's used Magma in the last week. or used to.
Yeah, I mean, I was at the Arizona Winter School, and there were like tons of students, and maybe 70% were using Sage, 20% were using Magma, and occasionally you would see Wolfram Alpha.
Anyway, I better go on to Sage because I've only got 5 minutes left. Anyway, I'm not going to say an awful lot about Sage because, well, sort of needs an introduction in a meeting like this, I think. Everyone knows the story about how William came to start up Sage. And if they haven't heard it, then there are places where you can read it. It's very entertaining. So you all know what Sage is. So here's what Sage is. Integrated together into a seamless whole which builds easily on any computer to do anything which any other package mentioned here can do. Well, not quite. But, you know, that's the idea. So I do want to say a few sort of personal things about Sage, though. Why is Sage different and why do I like it, sort of say. I've been trying to think of what I don't like about Sage, but I haven't come up with anything yet. Anyway, why is it different? Well, it has this philosophy not to reinvent the wheel. You take what's out there that's good, both good and free. Free in the sort of open source, is it beer or speech? Anyway, both. Speech sense, and put it together. Often this code is much easier to build and use than it was before. If you want to run my program to do 2 descent on elliptic curves called W rank, I will say install Sage. It's much easier than the configure and build scripts that I used to try and maintain. Okay, it's different. It uses a mainstream powerful language, Python, instead of creating its own. This is a comparison with both GP, which is its own language, and Magma, which is its own language. It's very easy to do experimentation. It's easy to use interactively. You can do things fast by having compiled code using Cypher, which we'll hear about. You can choose whether to use it as a command line or the graphical interface, the network interface. And you can run a server, and anyone can use it. So it's good for teaching classes, etc. And it's got large and active group of developers, more coming in all the time. I think the rate of arrival exceeds the rate of departure, which of course is not 0, but and you have this nice, easy transition from being a user of Sage to being a developer. So it's very easy to think, oh, it would be good to have this in it. You write a function, get other people to help you improve it a little bit, and then it gets in there. And that's, I think, really good. It makes people feel that it sort of belongs to them. I think that's important. Rather than being some kind of remote thing where people might listen to you and they might put the code in. And it's free in all senses. How many of us are in universities where undergraduates are encouraged to pay $10, $20 for a cut-down version of Maple?
It's more than $10.
Is it? So why do I like using Sage? Well, all the reasons on the previous page, of course. I should say, before I go through my list of reasons for liking Sage, I still write a lot of C++ stuff, because I've got a lot of code written in C++ that isn't all wrapped in Sage yet, let alone rewritten. And I still do use, I think I probably hardly ever use GP anymore, except to help debug the bits of GP that are in Sage. I do still use Magma a bit. So certainly more powerful than anything else that I've mentioned before. I like that I can use it to collaborate with students. If I've got students writing a bit of code, then I get them to do it in a notebook, and then when they come, they can share it with me, and they come to my office and we do it together. I mean, it's a small thing, but I find that makes it really easy. They used to come into my office with printouts of what they were writing. This is much easier. I like the fact that it can interface with other programs and the operating system. And I'll give you one example of that, something that I'm doing at the moment. I've got this set of programs called EasyLib, and one of the things it does, these programs do, is find modular elliptic curves. And when EasyLib has found all these elliptic curves, there is a lot of what I call post-processing, things you want to do with the curves once you've found them. find the complete isogeny classes, find their Mordell rate generators, find the integral points, find lots of data related to the work through dye conjectures. And I used to have horrible kind of scripts running these and managing files and so on. I now have a Sage script that does this. And most of the computation of this post-processing is done actually within Sage itself. Although there is one thing that I call Magma for. But fine, I can. I've got Magma, and Magma can do that, so I use it.
Do you use the Sage interface to Magma?
Yeah. If I've got an elliptic code that I know has rank 1, because it has analytic rank 1, and if I don't find a point of infinite order quickly by searching, I just call Magma's. Just quick, easy, and automatic, and it's really good whether the point is that size or that size. And lastly, I like the fact that when I write code for Sage, I have the feeling that this code is going to last. I hope it does. Instead of just kind of rotting away. I mean, how much time have I spent in the last 40 years digging up some old program I used to have and finding it didn't work anymore and trying to get it to work and so on and so forth, and thinking that, if I fell under a bus this afternoon, no one would ever be able to get that stuff to work ever again. Whereas somehow by putting stuff into Sage, I get the feeling that it's got a much better chance of surviving, as long as it has a right to survive, which is until it gets exceeded by better stuff. So those are some of the reasons I'm using Sage. I haven't come up with a negative yet. Well, I'm still trying to get something. It's after 10:30. I just thought I'd better mention one. There are lots of packages that I haven't mentioned here because it's partly because it's a personal talk and partly because it's been focused on number theory, so I haven't mentioned that. But I'll mention a few of these. There's masses of other packages around for doing multiples in an integer. I mentioned GMP already, so I thought I'd better mention MPIR, but there were others. There were lots of these. I can't remember all their names anymore. There's another big package for algebraic number theory called Kant, developed by Michael Post and his group now in Berlin. I don't think it's now being actively developed. It's a bit hard to tell. Their webpage hasn't been updated for over 2 years, but it's got a library, command line interface, and a web interface, which I think you know developed for this, and a lot of the algebraic number theory functionality in Magma. So for a long time there were these two packages, PARI and Kant, who both did algebraic number theory, completely independent implementations, often using completely different algorithms. It was good to have both of them because you could be more confident in results when you computed them independently. And the other one, and this is another, this is the last thing I'll say, because it's really a good illustration of what can go wrong in a sense. There's this package called ZMAT. The SI stood for Siemens, who funded it. It could do a lot of things. It could never do quite all the things that Zimmer claimed it could do. I being recorded.
Yes.
Wow. Anyway, but he had a lot of students and assistants who worked really hard implementing algorithms, developing algorithms, implementing them, putting into this package, and it's now completely unavailable. He retired.
Oh, they passed it off to NZ.
They passed it off to these Japanese people in ZMath, but
There's no overlap of code.
there's no overlap of code. NZMath is now trying to start off from scratch and reinvent the wheel, and they're not getting very far.
They've been writing stuff in Python for 6 years
Yeah.
or more.
And so, I knew a lot of the people who worked in that group in Saarbrücken, and they did a huge amount of work, and there seems to be absolutely nothing left of that work. That's really sad. So, let's organize Sage in such a way that that never happens.
Was CMath closed source or just like a weird license? Because I seem to recall trying to build it and failing miserably once, but maybe
there were licensing restrictions imposed on them by Siemens. I think it was free for academic use, certainly. So I did download and build it occasionally. I co-supervised a student of Zimmer's who was writing actually 2 descent on elliptic curves over real quadratic fields in ZMath, and I could run that code for a while. No, I think you got all the source.
Okay. It's just a weird license.
Yeah, it was a weird license because of the commercial sponsorship. Cool.
more questions for John? Any questions for John? Okay, so how about if we do introductions at a quarter till, so at 10:45. Okay. And in the meantime, there's lots of refreshments up here and stuff. It's all set.
Including blackberry sage.
Yes, blackberry sage. And there's a tea kettle here. Somebody wants to get it going.
Tea for wisdom.
And there's also hot water here. That must have been filled with water. They try to be so somewhere out there.
It's going to be on Friday.